Okay, so in the last couple of videos, we've really focused on single replacement reactions, and here we're going to focus on double replacement reactions, those reactions which oftentimes will form a precipitate. And the picture right here is a very typical precipitation type reaction. Look at what is inside the four ions that are inside the solution, the two solutions that are being mixed. So the first solution is potassium iodide, and you'll see there's a free-floating potassium ion and a free-floating iodide ion, right? Because ionic compounds dissolve and dissociate. And here's lead 2 nitrate, and you can see free-floating lead ions and nitrate ions. And then what happens is the positive of one, so the potassium, is going to possibly combine with the negative of the other. That's our KNO3 over here. And the other ion, the other compounds that may form, the positive of one and the negative of the other, and that's the other ionic compound that forms. Now in this case, the lead iodide that forms is insoluble. It does not dissolve in water. It forms a solid, which we call a precipitate. And we saw this when we did the lab a few chapters ago with the drops of solution on the piece of saran wrap. And sometimes you saw something that was sort of milky or it was opaque, a little chalky. And that's what the lead iodide is there. You can see it's bright yellow, but it's not dissolved. It's not a clear translucent solution. It's sort of chalky in there. And this is a very common type of reaction called a precipitate reaction. So the first thing we're going to learn is how to just figure out what the products are. And then we will eventually get to figuring out whether those products are solid or aqueous. So in order to figure out what the products are, we have to first make sure that we understand what ions are actually floating around in solution. So write the ions that make up the reactants. Then we take the negative of one and positive of the other, make the new compound, really taking into account the charges of those, like actually crisscrossing to get the new compound, and then finally balancing. So we only balance at the very end. So if I take a look at these couple of examples here, right? Sodium carbonate and calcium nitrate. So first of all, we got to think what ions make up these. So sodium has a +1 charge. I know that from the periodic table. Carbonate is one of those polyatomic ions that I've memorized. Calcium is 2+, again, from the periodic table. And nitrate is NO3-. Again, I've memorized that polyatomic ion. Now, positive of one, negative of the other. So this would be sodium and nitrate, +1 and -1. So when I crisscross the charges, I just need one of each, NaNO3. And then for the other compound, positive of one, negative of the other. Now, if the positive ion always comes first, so I don't do CO3Ca, it's going to be CaCO3, and because it's 2+ and 2-, again, I just need one of each. And I'm not going to worry about whether they're solid or aqueous quite yet. Balance. So now that I have the products, balance. And all I need to do is put a coefficient of 2 in front of there to balance out the sodium and the nitrate. Maybe try the next one on your own or follow along. Magnesium is a 2+ ion from the periodic table. Sulfate is 2-, I memorized that. Na +1 OH-, right? Positive of one, negative of the other. Crisscross the charges, Mg parentheses OH2. All that stuff from chapter 7 in the ionic compounds we still need to know. So this is going to make magnesium hydroxide, and the other compound that will be formed is sodium sulfate. Again, crisscross the charges, Na2SO4. Now that I have the products, I can balance. I'm going to need to put a 2 here to balance out my sodium and my hydroxide. So that's how we predict the products and then balance. And now we have to figure out what is going to come after these, solid or aqueous. Oh, actually, before we do that, these reactions will only happen if they actually form a solid product. If everything is aqueous, then did a reaction really even take place? So these double displacement reactions will only occur if a precipitate forms, if one of the products is a gas, or if one of the products is like water, which does not dissociate. So we're going to go through each of these three examples, focusing mostly on that first example of the precipitate one. So now we're just start reminding ourselves a little bit about what we know about solubility, right? A solute is the substance that is dissolved, where solvent is the substance that the solute dissolves into. Solutes and solvents come in many forms and types, but often in chemistry class, we talk about water in aqueous solution. Aqueous means dissolved in water. And when a solute dissolves, the solvent molecules, so usually the water molecules, surround the solute particle and form what's called a hydration shell, with negative side of water surrounding the positive ion and vice versa. And some solutes, such as ionic compounds, break apart into the ions when they dissolve. We call that dissociating. So if you look down at the bottom, you'll see before dissolving, we have the solute, the potassium hydroxide, solid, and we have the solvent, which is the water. And then when I mix them together, the potassium hydroxide dissolves and dissociates, right? So you can see here's the potassium, here's the hydroxide, and look at that hydration shell that's going on, right? The positive ion is surrounded by the negative, the partially negative side of water, and the negative ion is surrounded by the partially positive side of water, right? Opposites attract, they surround those oppositely charged ions, and that's what makes the solution. Okay? Some compounds are soluble, some compounds are insoluble. When we talked about ionic compounds at first, we said ionic compounds dissolve in water and they dissociate. And then we did that lab with the drops and you saw, well, sometimes they do and sometimes they don't. And I asked you to come up with some general rules for when they do and when they don't. And this is when we're actually going to learn them for certain. So when a substance does not dissolve or doesn't appear to dissolve very much, we call that insoluble. And when an insoluble substance forms during a reaction, we say a precipitate forms. And you can look at it in the picture here. Silver chloride, AgCl, is an example of an ionic compound that scientists consider to be insoluble. Very little silver chloride will actually dissolve under standard temperature and pressure. We can change solubility with temperature. We'll talk about that in another chapter. But look at the particulate diagram, right? The AgCl is staying in its crystal lattice, right? It's staying in that rigid geometric pattern. It's not forming any hydration shells. The water is completely separate from it. And if we were looking at it, right, you would actually see silver chloride. It's white. You would see white powder forming on the bottom of the beaker, as opposed to something such as sodium chloride. When sodium chloride is in water, we know that it is soluble. And it says NaCl is an example of an ionic compound that scientists consider soluble. Lots, almost 100% of it, will dissolve under standard temperature and pressure. And again, we could change the amount. But here you can see that the hydration shell does form. So the positive side of water surrounds the negative ion and vice versa. And when you look at it, it actually doesn't look like really anything. It looks, salt water looks pretty much exactly the same as just regular water. It's hard to even see. So this is what happens when we mix two solutions together. When a scientist takes two solutions with dissolved and dissociated ions, like we did with those droppers, and mixes them, the new solution contains all of the ions from the two solutions. If two of the dissolved ions together make an insoluble compound, we say a precipitate forms. And you'll see that at the bottom of the solution. That was when we saw the drops, form like a cloudy sort of mixture. The liquid above the precipitate is called the supernatant. Think of super means above. So if you look at the picture in the two test tubes, we have potassium sulfate and we have calcium chloride. And when I drew them in there, I drew them aqueous. So I drew them actually dissociated, because when it says aqueous, we know that ionic compounds aqueous in solution, they are not together, they are dissociated. And then when we mix them together, look at what happens. The K plus and the Cl minus are still floating around in what we call the supernatant, but the calcium and the sulfate have come together to form this ionic compound down there that's solid. So you can see it actually, starting to pile up on the bottom of the beaker, and that is the precipitate. And we have different ways of writing what we just did, okay? What we just wrote, or what is written here for us, is called the complete balanced chemical equation. So you can see it lists the reactants, and I color-coded these so you could see the positive of one matches up with the negative of the other. So the pink K and the pink Cl come together to make KCl, and that is aqueous. And then the blue calcium and the blue sulfate come together to make calcium sulfate, and that is the solid. We'll learn how to tell aqueous and solid in the next video. So that's the complete balanced chemical reaction. There is something else that's called the complete ionic equation. The complete ionic equation means show me just the ions as they are in the solution, which means if they're aqueous, show them to me separate. So anything that's aqueous, we actually show dissociated. So instead of writing K2SO4, I'm going to write them separate, and I really need to pay attention to how many there are. So when K2SO4 dissolves in water, it dissociates. What does it form? Well, it forms 2 K plus ions, so I'm going to write that aqueous, and 1 SO4 2 minus ion. When calcium chloride dissolves in water, it dissociates to form 1 calcium 2 plus ion and 2 chloride ions. And what does it form? Well, the 2KCl is aqueous, so that's also dissociated. So 2K plus and 2Cl minus. Remember, this 2 applies to both of them. And then last, calcium sulfate is solid, so we don't break that apart. CaSO4 solid, that stays together. So that's called the complete ionic equation. It shows a little bit more accurately what's really going on. And what we will notice right away is that, hey, look at this K. Did the K actually do anything? Did it change at all in the reaction? No. The beginning of the reaction, potassium was floating around. The end of the reaction, the potassium was floating around. Potassium really didn't do anything in this reaction. It didn't change. We are going to call that a spectator ion. Same thing happens with the chlorine, right? The chloride ion in the beginning is just floating around. In the end, it's floating around. So did it really change at all? No, that's another spectator ion. So what we can do is write what we're going to call the Net Ionic Equation. This is where we show the ions that react to form the precipitate. So in this case, we would get to cross off the spectator ions or leave them out, and only write the ions that actually go into making the precipitate. The precipitate was, of course, calcium sulfate. Another example of this, write the net ionic equation for the precipitation reaction that occurs when sodium chloride is mixed with silver nitrate. So, number 1, figure out which ions will form an insoluble compound. So what are the 2 possible products? Well, we have, let's see, sodium is +1, chloride is -1, silver is +1, nitrate is -1. So my possible products are NaNO3 and AgCl. Like I said, we're going to learn in 1 second how to tell which one is aqueous and which one is solid. It's that silver chloride that was solid. You might remember when we were doing that activity, most people came to the conclusion that its transition metals are often insoluble. You may have also learned that all the sodium ones were always soluble. So to write the net ionic reaction, all I have to do is show the precipitate forming, I should say. Silver ions plus negative chloride ions, got to have the charges in there, making AgCl solid. right? We have to show the ions that are forming because this is called the net ionic equation.